All right, so we have a triangle with circumcircle omega and in center I. Let me check the chat. So let's draw the in circle. All right. So we have D, E, and F. And then I is the in center. L is the midpoint of arc BC. And then EF meets BC at G. So B, D, C, and L are harmonic. Or B, D, C, and G are harmonic. Then we draw the circumcircles of GBE and GCF. Oops. So those triangles are similar, right? GBE and GCF. Actually, I'm not sure about that. No, I don't think they are. But they meet at a point K. And then we draw the circumcircle of DKL. And we see where it meets BC and AL. So it meets BC again at P, and it meets AL again at Q. So this is P, and this point is Q. So let me make Q a little easier to see. So this should be Q. It's hard to draw it. There we go, that's better. So that's Q. We want to show that PQ bisects AG, BE, and CF. So that's 3 different segments. Let's see, what if I make this like a tall triangle? Like a very tall triangle or something like that, and then I shrink it. I think that looks good. Okay. But then P and C are too close. Yeah, I kind of like that. Okay, so try to make the best diagram possible. So that looks good. DK, we draw DKL, and it meets it at P and Q. Are GK and AB perpendicular? Let's see. That's AB. And I don't think so, because I think IG is perpendicular to AB. Let's see. Oh, but maybe GI and K are collinear. It didn't. Yeah, no, it's not true. So IG is perpendicular to AB, but it doesn't pass through point K. So yeah, I could just draw IG. I is a knot on the circle though, even though it looks like it in that picture. So do we want to first show it bisects AG? Or so isn't
I
that,
think we should do AG first because BE and CF are the same. I think.
yeah, basically we're showing that PQ is the Gauss line of this quadrilateral, right? Yeah, that's all we're trying to show that PQ is the Gauss line of this quadrilateral. Okay. And okay. So yeah, I could draw the midpoint of AG. And I think, isn't there something special about the Gauss line with areas? I think in my video I did like a proof of the Gauss line. It's like if we can show, like for every point on the Gauss line, it's like the sum of the areas of BQC and FQE are the same. I think that's what it is.
I don't know if it's true, but it looks like PQL. I mean, DLK is tangent to. No, actually, no, it's not.
Ah, okay. Yeah, it almost looked true. Yeah. So I think it might be true that, let me think about this. I think the area of PEF might be half the area of BFEC. I think I can actually check that with GeoGebra. Does it have a way to do area? It does. That's weird. So the area of PEF is 8.93, and then the area of this, let's see if my idea is right, 17.86. Yes. So if we can show that the area of PEF is half the area of BFEC, and then we could also show that the area of QEF plus the area of QBC is also that same number, that would be a way of proving this. Although it's maybe a little bit hard to do it that way, but yeah.
Can you write it down, like just for easier follow?
Yeah. But yeah, I don't think that's the best way to do this though. But so if we can show that the area of PFE is half the area of BFEC, and Q the same thing. If we could show both of these, that would solve it. Although that looks like it's probably hard to do. So yeah. I think it's probably easier to, because we know the three midpoints are collinear because they all lie on the Gauss line. So we could pick two of the midpoints and show that P is collinear with them. And then, yeah, I'm not sure. Yeah, so if the problem is true, then these two both have to be true. Okay, so this is a circumcircle DKL. It almost looks like Q lies on it, but I don't think that's true. I think that's just a diagram. Like, does Q do? Oh, we defined Q to lie on it. So yeah, it has to. Maybe there's some other circle through P and Q. So like we could show that H lies on the radical axis of some other circle. Let's see. PQ, PQI, maybe it's circle PQI. So I wonder if these all, yeah, I think that's a coincidence. I don't think they actually concur. Yeah. It just looks like it. What about PQG? Is there anything special about that? No. So isn't there some other proof about the Gauss line using like orthocenters? Like you draw like the circles with diameter BE, CF, and AG, I think, right? And I think you show they're all like coaxial or something. So maybe,
Yeah, and then we prove that the its radical axis is the line connecting the orthocenter of AEF and ABC.
okay, so it's connects the orthocenter of AEF with ABC.
Yeah.
Okay, that would be the radical axis of all those circles. So that would mean that PQ is perpendicular to that line, right? Connecting the two orthocenters. If the problem is true.
Yeah.
This is going to be a little messy, but I just want to see what that looks like. I'm curious. So we have this circle and this circle and this circle. And they meet at these points. And those are perpendicular to PQ, basically. So yeah, I'm going to erase this. I know this is really messy, but it's interesting. What was J? I forgot what. Oh, J was the midpoint of BE. Interesting. Might get a drink. All right, got a little snack and a drink. Yeah, this one's tricky. It just seems so random. Yeah, how would we begin here? I don't even know where to start. So I mean, I wonder if it has something to do with the Mikael point of BFEC, right? So is AKEF cyclic? No. So, I mean, Mikael's theorem says that GFB, GEC, sorry. AFC, oops. AFE and ABC all concur. So yeah, I don't know how helpful that is. Yeah, it looked kind of like the Mikael point. So yeah, you have the intersection of these two, but it's maybe it's worth intersecting. It's like draw the Dragon point or the Dragon point. So I think we can try to use Mikael's theorem. Like, is there another cyclic quadrilateral? So KFE is similar to KBC. KEF is similar to KBC. Okay. Because KEF is KEG, which is KBC. So yeah, we have a spiral similarity that takes one to the other. So yeah, KJEF is cyclic and BJKC is cyclic. So yeah, these quadrilaterals are similar. Now P and C look super close again. I feel like now that we know that J lies on both those circles, maybe that might help a little bit. Yeah, we could try this for like another 15 minutes and then move on. Or yeah, like at 11:15, I can move to another problem if we don't find anything. Yeah, it looks interesting though. Oh, Iranian Geometry Olympiad. Was that like a really hard problem? I'll have to check it out. Let's see. So I wonder if I did that on my channel yet, because I did the IGO before. So but yeah, it's like the first one on this website. So let me scroll to the bottom. Oh, but this is like, was it like the advanced level? This one, right?
Yeah.
Oh, that looks interesting. P and Q. Okay, so you have like AD is the Euler line. That looks pretty interesting. So yeah, maybe I'll try to do it because I'm guessing you guys already saw it, but I'll try it sometime after the session if I have time. Oh, we did P3, but not P5. All right. Yeah, this one just looks so hard. Like I just don't. Yeah. Like P and Q are just defined so randomly. Like you're intersecting with AL and BC. Sometimes it helps draw LD and let it intersect with the circle. But for this problem, I don't know if that'll be helpful. Because, I mean, if we let LD intersect the circle again, whoops, then we know A, F, I, E are cyclic with that point. In fact, I think it, let's see. So yeah. Exactly. So they meet here, but I don't think that helps with this problem. So let's see. I still. So PQA. Is there like something special? I don't, is anything hard, like maybe we could project through like H or so what if it were true that they were collinear? Okay, let's say we projected through Q onto this circle, right? So if it were true that they were collinear, then H should go to P, A goes to L, and then G, let's see where G would go to. And then we could do the point at infinity. So we would have P, L, N, and then let's draw the parallel to AG. We could try to show that that's harmonic, PNOL. Although that doesn't seem that easy to show that. So yeah, let's just check that. Yeah, that's true. But yeah, I don't think that makes things easier, really. Or we could try projecting through P instead. Is OD equal to OP? Let's see. No. Yeah, let me erase some of these points for the time being. Yeah, I'm gonna get rid of point M. I don't think it's very useful. Oops. Sorry. So what was I doing? So first I tried projecting through Q. What if I project through P? So H goes to Q, G goes to D, and we can see where A goes. So we have QD, A goes to that point, and then the point at infinity. Go to here. And maybe there's something special about this. So M, let's see. I doubt that that's concurs on the circle. Yeah, no, it doesn't. So MK, anything special? Um, Yeah, no, this isn't going very far. So we have QD, this point. Yeah, I don't think it's going to work, this idea. Is AD tangent to KDL? Let's see. It certainly looks like it in this picture. I wonder if it is. Oh, it's not. Okay. Yeah, they're just slightly different. Yeah, it's not. All the emojis just look like a rectangle when I look at it, unfortunately. So I don't know what emoji it was, but yeah. It's a crying one. All right. Yeah, this is a deep configuration. You can look at it for like 5 more minutes and then I'll move to a different problem. Yeah, I don't know if there's some special property of the Gauss line that I just don't know about. Could be though. Got to take more use of the point K. Yeah, because we have 4 different circles passing through K. Maybe we can use inversion. I'm always scared to use inversion, but if we invert about, yeah, I don't know. Or maybe we could use the power ratio lemma. Yeah, a lot of circles passing through K. EJKC, EFJK, GBKE, GFKC. Yeah, and we never really used, I mean, there's this circle, right? centered at I. So yeah, maybe I wonder what happens if we invert about that circle. The midpoints of the Jirgan-Chebians. So like how, or I don't know. Or what were you thinking with that? Because I guess then HM is parallel to GP. All right. All right, I think let's move on to a different problem. So yeah, here are the problems that I was looking at. This one looks kind of interesting. I'm not sure if it's that hard. Let me just take a look through the rest. This one also looks kind of interesting. So ABC is inscribed in a circle center O, and so D is the touch point, and then M is the midpoint of DC. Okay. So what is G? So yeah, this one looks interesting. Or we could do, we did that one. Let's do this one. So we have Y and X. Yeah, let's try this one. All right. So we reflect the circumcenter over the three sides. All right, so we draw the circumcenter. I mean, we don't even need to draw H, right? Okay, so I'm going to reflect it over each side. So it's D, E, and F. So DEF is, I think, is it congruent to ABC? I think so. Yeah, because DEF should be congruent to ABC, I believe. So yeah, it starts to become clear if you draw like the midpoints of A, B, B, C, and CA. Okay. And AE and AF. Oh, did we do this problem before? It looks very familiar. I think we might have. Let's see. Okay. So they're reflections across the 9-point center. Okay, so this is P, and then we draw AE and AF. We see where they meet BC. Zoom in a little bit. So N and M. And BD and CD intersect. Okay, this figure is going to be a little tricky. We got to intersect BD with AC. Yeah. Okay, so I'm going to have to shrink it and move some things around. So is it better for this to be a flat? Yeah. That looks pretty good, actually. I think. So this is X and this is Y. This up and this down. There's X. We want to show that P lies on the radical axis of B and Y and CMX. Okay. Let me hide a bunch of things. We don't need. I'm going to draw it back later. Okay. And is that everything? I think so. So basically, if we draw this circle CMX and B and Y, then we're saying that P, okay, so maybe the altitude like passes through the intersection points. So then, yeah, so really we just want to show I mean, forget point P, we just want to show that the perpendicular from A, we just want to show A lies on the radical axis of those circles. And then we want to, pick any 2 points on the altitude, and we want to show they lie on the radical axis.
Do the two circles meet at the orthocenter?
Oh, that's a good point. Let's see. I think so. Yeah, they meet at the orthocenter. So yeah, basically if we draw the orthocenter, we want to show that we get a cyclic quadrilateral. So basically I'll let H be the orthocenter. And then can we show that MHCX is cyclic? Yeah. So is the orthocenter, is this the circumcenter of BEF? Yeah. So the orthocenter of ABC is the circumcenter of BEF. Because, yeah, like maybe I should just draw the midpoints of A, B, B, C, and CA. So yeah, we have, so yeah, O is going to be the orthocenter of this. So by symmetry, H is the circumcenter of this, of BEF. It's interesting. So could we first show, can we show that AC times AX is AB times AY? So can we show YBCX is cyclic? Oh, that's not true. I thought, what? So wait. We want to show A has the same power with respect to CMX and BMY. So that is the same as saying AC. Isn't that, don't we need to show that AC times AX is AB times AY? I guess I'm confused. Am I missing something? And wouldn't that mean that BYCX is cyclic? What am I missing here?
Sorry, but can you repeat?
Oh yeah, so let me check the chat. X and Y are wrong. Okay, did I draw, so BD cuts AC at, oh, I flipped X and Y. Oops. So this should be Y and this should be X. Okay. So really, it's really these circles. B and Y. Huh. So did I just do the wrong circles? Because like, yeah, I guess it's really those circles. So we accidentally came up with a true problem, I guess. So I guess P lies on the radical axis of those circles, and it also lies on the radical axis of the other two circles. That's weird. but even still, is it true? So even though like it looked like I got a contradiction, so before I was doing this circle, so before I had X and Y mixed up, so it was like this and this, right? So I wonder, does this pass through the other point of intersection? Oh, it doesn't. So that's where I got confused, because I have this circle and this circle. Wait a sec. Oh no, not that. I have this circle. And yeah, okay, so that's just wrong. Okay. So I need to show P lies on the radical axis of these two. Yeah, maybe I could make it look more like symmetric. Sorry. I guess it's never going to be perfect, the diagram. Interesting. Okay, so I want to show it has the same power with respect to those. Let's see. So H and P are reflections across BC. Like, what if we reflected these two circles across BC? Would that be anything special? So, let's see. So I'm going to reflect this circle about line BC and this circle about BC. And then I could try to show H lies on that. But if I reflect X across BC, is X prime, can we say anything about X prime? Yeah, I don't think we can say, oh, are X prime O and C collinear? Yeah, because X prime B and C are collinear. So X, D, and C are collinear, so X prime O and C have to be collinear. I just don't know if that helps that much. Yeah. And yeah, and then we could reflect A over BC. So yeah, we could do a bunch of reflecting here. But I don't know if it helps really. So I'm just going to undo all that. You guys want to try an easier problem, or you want to keep working on this?
I think we should keep working on this until we solve it.
Okay. All right. So even if I mean, it's still an interesting fact that like MHCY is cyclic. I don't know if we'll end up using that, but can we prove that? So that's cyclic? Is there an angle chase? So we'd want to show that angle HMY is HCA, which is 90 minus A. So HMY let's see. You're back. All right, I am back. We have BNY, CMX. So yeah, the most obvious thing is to show that P is the same power with respect to both circles. Can we use Casey's theorem? That's what I'd like to do. I'd like to use Casey's theorem. I'm just not sure how. Maybe if we draw the centers of these circles, it'll show something. Yeah, they're not the same size. So one could be bigger and one could be smaller. And if I connect the centers, it doesn't really show too much. Oh, you know what? Maybe. So like I saw before that MHCY is cyclic, right? So what if I use Casey's theorem and I take the difference between the powers of P with respect to these two circles? Actually, you know what? I wonder. So we know MHCY is cyclic. And we know B, but I don't think they have the same. Yeah, they don't have the same circumradius. But let's see. So this and this. Yeah, it's not gonna work. If I reflect this circle about that line, intersects it here. I think maybe you just need to use Casey's theorem in a really clever way. Okay. Is there some special line through P where we could use power of a point more easily? What if we reflected this across P? No, yeah, PD and N can't be collinear. Yeah, how do I find the power of P? I doubt that these concur, but let's check it. Yeah. Yeah, Casey's theorem kind of seems like the most straightforward way. I personally like using Casey's theorem on these circles, on this one and this one, but there's still be a lot of work. Is CX parallel to BO parallel to AM? I would be very surprised if those are true, but let's check it. In this picture, it looks like it, right? Wait, did we just miss that? Yeah, it looks like those are definitely parallel. I don't know if that's obvious. It's a simple chase. Okay. Yeah, I guess we just missed that. Okay. Well, yeah, because BOCD is a kite, right? So I kept thinking D lies on the circle. Yeah. BOCD is a kite. So BO is obviously parallel to CD, or it's a rhombus, not a kite. Yeah, a rhombus, yeah. But AM, yeah, it's probably just an angle chase because, yeah. Because angle AFE, yeah, I think I see it. I wonder what we get if we draw the parallel through P. I don't think it's anything. See, what about this? Or this? All right. BNY and CMX. Yeah, let me see if I can prove MHCY is cyclic. How would I do that? So I want to calculate angle HMY. That's tricky. Basically, I want to show angle HMY. I want to show it's HMC is HYC. It's already 11:56. Wow. It's problem on by fast. So what were some of the similarities that you said you saw? It's a good problem. Yeah, I just like this sub problem trying to show that MHCY is cyclic. I wonder, so MHCY and NHBX. We reflect everything across BC, then that's like showing we want to show MPC and at some point appear as cyclic. It's tricky. All right. One more minute.
I think I have an idea using similar, but I haven't completed it yet. I will send maybe after this session, I will send my solution.
Okay, sounds good. Yeah, I'd love to see it. All right, so I think I'm gonna stop here because we're out of time. But yeah, if you find it, post it on the Discord because this seems like a really cool problem. So thanks everyone for staying this long, and for everyone watching on YouTube, thanks for watching. So if you'd like to join us in the future, feel free to email me at mgreenb801@gmail.com. It's in the description of my video. We meet every Sunday at 8 a.m. US Central Time. So yeah, we had a few easier problems on this session, but a few super hard ones. So yeah, it'll be interesting to see after the session what we come up with. So thanks again for watching and have a great day.